So hello again, and welcome to today's SCOPE webinar, which is part of our continuing series featuring Yukon University research chairs and leaders. We're hosting this talk with respect and gratitude on the traditional territory of the Kwamlin-Dun First Nation and Ton-Quechin Council. My name is Sabrina Kinsella. I'm the Acting Senior Science Advisor for the Yukon government. Our first speaker today is Dr. Joel Cubley, Geoscience Instructor and Chair of the School of Science at Yukon University. Hailing from New York originally, he moved to Canada in 2006 to complete his PhD at University of Calgary. And he joined the university, or at that time, Yukon College team in 2012. You can read more of his bio in the newsletter or on the YukonU site, but I'll keep it brief for sake of time. Today, Joel will speak to us about his involvement in collaborative research that uses geochemistry, geochronology, and fault motion restorations to better understand plate geometries and geologic environments of Southwest Yukon in the Mesozoic era. I know we're all eager to hear more, so I'll turn the mic over now. Welcome, Joel.
All right, and thanks, Sabrina, and thanks to all of you for joining this afternoon. Whereas Yukon University is very much a teaching-focused institution, and we take pride in that, there are many faculty members that have active research projects, and it's nice to have an opportunity to highlight some of that today. Like Sabrina said, I'm going to be looking at mountain building in Southwest Yukon and how we can use geochemistry and geochronology of rocks to get us to understand sort of larger questions about the amalgamation and the formation of the Canadian Cordillera. And so just to jump right into things, I'm going to share my screen quickly. The critical first step. Here's a simplified map of the Yukon and geologic terrains within the Yukon. For those of you who aren't familiar with that term, a terrain is just a crustal fragment of rock that has some unique history to it and a distinctive sequence of geologic units. So essentially, it has a different origin and a different history than the terrains around it. In the Yukon, there's a fundamental break basically that mirrors the trend of the Tintina Fault, which runs from Dawson down to Watson Lake. To the northeast of the Tintina Fault, most of the rocks originated in sort of the edge of a continental margin. So sediments being washed off of ancestral North America into basins and carbonate reefs. To the southwest of the Tintina Fault, you'll notice that there are a much greater number of these geologic terrains. There's more colors, there's more action. Essentially, this is the heart of the North American Cordillera, and it represents a number of volcanic arcs that have collided with the North American margin through time. And I'll use the term volcanic arc quite frequently during this talk, but what a volcanic arc basically is, or a modern analog, would be something like the Philippines, Indonesia, etc., where I have oceanic crust that is essentially subducting under other oceanic crust. What we're going to be looking at today is this southwest corner of the Yukon, so southwest of the Tintina Fault, where there are all of these geologic terrains, and we're going to be thinking about how those terrains actually collided with the continent, the timing of that, and sort of the mechanisms for that collision. And this is the bread and butter of geological survey geologists. And Maurice Colpron, who's the head of bedrock geology at the YGS, just released a new paper within the last few months, looking at the collision of these terrains with North America in what is known as Mesozoic time. And I'll throw out the term Mesozoic frequently as well. The Mesozoic basically is Triassic, Jurassic, and Cretaceous time. And in these images, it ranges from about 230 to 165 million years ago. There's a lot that goes into the construction of these models. And what I'm going to do is just walk you through how you can take outcrop information and geochemical information and then scale that up to making some broader decisions about how we construct these large-scale models. And so the project I'll be talking about today is what's known as the Bear Creek Project. I think I made the executive decision to name it that, but it's a collaboration between myself and a number of folks, both at the Geological Survey, in industry, and then at other academic institutions. And back in the summer of 2014, the Yukon Geological Survey decided to undergo bedrock mapping in a field area that's shown by this red box right here, just northwest of Haines Junction, and west of the crossroads that is Bear Creek itself. The motivation for mapping here was just that there was a package of rocks, the Bear Creek assemblage, that was very poorly understood. It had historically been assigned to another geologic unit, but some preliminary investigations by Steve Israel had basically identified the fact that it didn't fit. And I mean, that's all well and good, but the uncertainty around the Bear Creek assemblage was amplified, and the importance of it was amplified by the fact that it sits on a major geologic boundary between large groupings of these terrains. So to the west of this field area is what's known as the insular superterrane, and these are rocks that are quite exotic to North America. So they have migrated or have moved from considerable distances before accreting to the North American margin. On the northeast side of that boundary, which is the Denali Fault at present, is what is known as the intermontane superterrane. And those are rocks that basically they have direct linkages to the North American continent at the time of their formation. They're known as pericratonic terrains. And so, you know, we have this fundamental suture essentially paralleling the Alaska Highway and paralleling Kluane Lake between these packages of rocks with very different histories. And so the Bear Creek assemblage might actually contain information that can really add to our understanding of this, the suturing and the sort of the accretion of the insular terrain. And you know, we've spent the last 6 to 8 years playing with data from this initial mapping project, revising our interpretations, and we hope to submit a paper on this actually in the next month or so. I was hoping it would be out in time for this talk, but timelines always get extended. And so jumping into rocks, this is what the rocks from the Bear Creek assemblage look like. They are basalts, and most of you are familiar with basalts just from Miles Canyon here south of Whitehorse. The Miles Canyon basalts erupted in what's known as a subaerial environment. So they came out of a fissure sort of up above Golden Horn and then flowed down into the valley. And there are characteristic textures that go with the subaerial basalts, including the columnar structures that we see at Miles Canyon. If basalts erupt on the seafloor, then there are characteristic textures in that environment as well. And the most characteristic texture is what is known as pillow basalt. And you can see in the upper left-hand corner here, those are basalt pillows. And it forms where I have very hot, greater than 1,000 degrees Celsius basaltic magma that cools rapidly in contact with cold seawater. And I have essentially, it oozes out and is sort of forced out into these pillow structures. And, you know, an outcrop at Bear Creek, you can see the remnant pillows in the lower left. But in the image on the right-hand side, those pillows are much harder to see. So here's a remnant pillow, here's another remnant pillow. The rocks are extremely, or not, I wouldn't say extremely, they're significantly deformed and they've been metamorphosed. So they've experienced heightened heat and pressure. There's been fluid that's been flushed through these rocks, so they've been hydrothermally altered. These do not look like the original basalts that erupted on the seafloor. And for our investigations, the metamorphism, the fluid flow is just a screen that we need to look through and get back to an understanding of what the initial eruptive environment was. And moving forward with this, and this is an intro textbook, first year geology textbook slide, but there's a number of environments on Earth in which we can have eruptions of subaqueous basalts, and different M members that we have to evaluate to understand where the Bear Creek assemblage came from. Just to point out some of the most common options, I can form mid-ocean ridge basalts, where in places like this in the South Pacific or in the middle of the Atlantic, where my seafloor is spreading and I have new basalts that are crystallizing at the surface. This is what is known as a MORB, or a mid-ocean ridge basalt. I can have basalts that are actually related to hotspots, or magma that's generated in the mantle and then comes up in the middle of a geologic plate. So that would be something like Hawaii, or Iceland has a plume associated with it as well. Or I can have subaqueous basalts in arc environments. And when I use the term arc, what I basically mean is that I'm in a collisional setting and one geologic plate is subducting underneath the other. So three kind of options that we would typically evaluate: a mid-ocean ridge, a hotspot, or an island arc environment especially. And each one of these is going to have some characteristic features to it. So how do we actually assign these basalts to one of those eruptive settings? Basically, this is based on trace element geochemistry. And trace elements are those elements in the rock that have very low concentrations, less than sort of 1,000 parts per million. And they're sensitive to geologic processes for different reasons. Maybe it's the fact that they have different oxidation states, and therefore are sensitive to redox conditions, or, I mean, it could be a number of different factors. But critically, if we choose the right trace elements, those trace elements can be immobile in hydrothermal fluid flow. They'll be immobile during metamorphism. And so they actually represent the original rock, where some more mobile major elements wouldn't. And so just looking at a couple of examples here, the graph on the left-hand side compares the concentration of titanium and vanadium. And you can see that the samples from Bear Creek give us a bit of an array that spreads out from, a typical mid-ocean ridge style basalt into something that's a little bit more enriched in titanium and has ocean island basalt hotspot kind of signature. On the right-hand side, again, samples from Bear Creek, despite the fact that I used a different fill this time, they seem to fall on this array between different mid-ocean ridge style, mid-ocean ridge signatures and a hotspot signature. And it just tells us that this magma basically came directly from a mantle source via partial melting, and it didn't really have any subduction signature. So both of these seem to rule out, the basalts being related to a volcanic arc, at least in their chemical appearance. You can look at this data in many different ways. My favorite way actually is just looking at what are known as multi-element diagrams or spider diagrams. But these consider a large number of trace elements. And essentially what you do is, you can compare the sort of average pattern for something like a hotspot ocean island basalt, or a normal mid-ocean ridge basalt, and compare your chemistries, which are the thin lines, versus sort of the expected values for the N member environments that you're looking at. And often you have all these different techniques that come together. You may not have one diagram may not give you a solid, surefire answer, but by looking at a collection of these, you get a sense about what your options are for an eruptive setting. And so just from this, the outcrop observations and the geochemistry, we can arrive at a few conclusions. We have subaqueous basalts that erupted in a marine setting. They have typically a mid-ocean ridge basalt chemistry, though there's variable degrees of enrichment. but there doesn't seem to be an arc influence. At this point in time, though, and just from what I've shown you so far, you have no idea how old these rocks are, and that's the next step, and where the field of geochronology plays into this. And so most of you, and especially those of you who are in Whitehorse, have seen the White River ash. It's distributed over the territory, and that basically represents an explosive eruption of Mount Churchill around 1200 years ago. The White River ash, in that ash, which I will call a tephra as a sort of a blanket term, inside that ash will be minerals called zircons, and those zircons contain the element uranium. Some of the isotopes of uranium are radioactive or unstable, and they will decay to lead. And I can use that decay scheme, uranium decays to lead, to actually date the formation of those zircons. The same thing happens in older rocks, but if that tephra has been lithified, so turned into a rock, it's called a tuff. And here at Bear Creek, you can see this light colored unit right here. That's a lithified ash or a tephra. It has zircons in it, and it separates two separate basalt flows. And we basically extracted zircons from this tuff. 4 of those zircons gave an overlapping age of about 204 million years ago. And that's essentially a latest Triassic age. What does that age actually tell us? It's not the start of volcanism. It's not the end of volcanism. It's in the middle of this period of volcanism, and where exactly, we're not entirely sure. But it at least allows us to give a pin, put a pin into when these were in the process of erupting. This is the scariest slide I'm going to put up here, but once I have an age and I have some information about the eruptive environment, I can go looking for other rocks in the Northwest Cordillera that have similar ages and geochemical signatures and may therefore be related. And just to point out too on here, many of you have been to Haines on the Chilkat Peninsula. There are Triassic volcanic rocks, the Chilkat basalt. And if I look at the data from the Chilkat basalt, it has basically a very good overlap with geochemical overlap and patterns with the lower Bear Creek assemblage. So geochemically similar with a similar age. And so I could say that, feasibly these are related to each other. If I look at other rocks, the Doghead assemblage is just on the east side of Kluane Lake. You'll notice that the Doghead assemblage has these big negative zirconium and titanium anomalies, which may reflect a volcanic arc setting. They're geochemically dissimilar to the Bear Creek assemblage, and therefore I have to think about a different environment for them to form in. And so this becomes sort of the game that you play with this data. Stepping aside from the basalts just for a second, this image in the upper left-hand side, this is a cross-section through part of this map area. The greens and dark browns are the Bear Creek assemblage. And we said that these were basically 254 million years old, give or take. Overlying those sediments, so up is this way, we have sedimentary rocks of various formations, the Jarvis assemblage and the Desias formation. And we can date the zircons that are in that sediment. So zircons are resistant minerals. They'll be eroded from an outcrop and then washed via, say, fluvial processes in a river into a basin. And then I can date those zircons in the sediment. In this case, the zircons that we recover from the sediment are all about 160 million years old. And that gives us essentially a maximum age for those sedimentary rocks. The maximum age, like the basin has to be, and the rock that forms has to be younger than the sediment that's getting washed into it, just from a basic timing relationship. And so, we can look at this cross section, we can say that these must be less than 160 million years old. And therefore, I have a gap in time of at least 40 million years between those units. And so this boundary right here, which doesn't look like much in the field, is actually what's known as an unconformity. And there's a 40 million year gap. There's missing time in that sequence of rocks. So one of my collaborators, Don Murphy, has been working a lot with fault restorations. And essentially how all these units match up. And the image on the left-hand side is sort of the configuration of different terrains in the Northwest Cordillera at present. And he's labeled all of the Triassic occurrences along that fundamental suture between the insular and the intermontane superterranes. And you'll notice that rocks with very similar chemistries, say the amphitheater, basalt in the amphitheater mountains and the Bear Creek rocks, are offset from each other by a significant distance. And what Don has been doing is he's been working to restore the displacement on major faults in that area, like the Denali Fault, which has hundreds of kilometers of displacement, and returning these rocks to their pre-faulting location to see how they would actually link up prior to that late overprint or shuffling up of all these rocks. And you'll notice that now in sort of the post-restoration example, so what would this have looked like in the Triassic? The amphitheater formation and the Bear Creek rocks line up quite well. And we can start to draw relationships between the rocks that have the arc signature separately from those that have the mid-ocean ridge basalt signature. The mid-ocean ridge basalt signature that we see at Bear Creek actually extends down into the sort of the panhandle of Alaska south of Juneau and in rocks called the Taku terrain. Where did this all go, and where am I taking this with our last few minutes here? How do we take all this information and actually incorporate it into a model? So I'm going to take you through a number of time slices here, 4 or 5 of them. We'll think about the information that we actually have so far and how that plays into this model. So in the early late Triassic, so 230 million years ago, basically I have oceanic crust in this ocean panthalassa that is subducting this way underneath a volcanic arc, something like the Aleutians with a chain of volcanic islands. And it includes this composite Wrangellia-Alexander terrain that I've called the sort of the insular superterrain. The Bear Creek rocks are not erupting yet. They probably wouldn't have erupted from 230 to 204 million years ago where they were dated. But there's other rocks of what's known as the Nikolai Formation that are flood basalts that are being erupted at this time. So that's just to set the stage. I have this chain of islands, volcanic islands extending out into the sort of proto-Pacific, and ancestral North America is over here labeled as Laurentia. If we step forward to sort of 206 million years ago, this is the core time of the Bear Creek eruptions. The Bear Creek assemblage would have been erupting off on sort of the distal inboard side, distal relative to the subduction zone, but the inboard side of this Wrangellia-Alexander terrain, far enough away from the subduction zone here that it doesn't have a subduction signature. But it's going to be some rifting of this oceanic crust. One of the things that we saw with, say, the rocks from the Doghead occurrences was that there's, in the middle of this basin that's behind Wrangellia and Alexander, I have consumption of ocean crust and a new arc that's forming in the middle of that ocean basin to give me some additional volcanism. And that's sort of a new linkage that we're making. If you go forward, so 174 million years ago, I've moved into Jurassic time. Maybe there's very little action in this basin at that point in time, but I still have subduction underneath Wrangellia and Alexander. I still have volcanoes. Those volcanoes are producing ash, tephra, et cetera, that has zircon in it, and will be contributed to future basins, sedimentary basins. In the early Cretaceous, so 130 million years ago, these terrains are progressively getting closer and closer to each other. There's a sort of yellow unit right here, which is those sedimentary rocks that are going to be deposited on top of the Bear Creek assemblage. And the zircons will come from that Rangelia Alexander terrain. That's where we have the ages to contribute those specific age zircons to this basin. We can also look at flow indicators and things like that. By 100 million years ago, in the mid-Cretaceous, essentially this inboard ocean, the Angiuchum Ocean, has closed. All of these terrains are in much closer proximity to each other. And this is before they get shuffled by all of the late sort of strike-slip faults like the Denali Fault. So critical thing with this, I don't want the takeaway message to be just that this is exceedingly complex and there's lots of arm waving with these models. But we've taken new observations and observations about these basalts at Bear Creek. We've fed them into a refinement of existing models to try to better understand these large-scale problems. And here are two images, one from Maurice Colpron, one from our study, looking at the exact same time period, but there are differences between these models that originate just from these new observations of geochemistry and the timing of some of these basalts, most notably the incorporation of this new sort of subduction zone and consuming that ocean in the Triassic. So I rolled through a bunch of Southwest Yukon geology very quickly there, but I am happy to take any questions with sort of the 2 minutes that we have before Tara jumps in. But if anyone does have longer questions, feel free to send me an email. My email's at the top. Thank you very much.
Thanks so much, Joel. That was great. Really interesting stuff. I feel like my knowledge may be quite basic, and so I'm afraid to ask you questions. I'm looking to the audience or in the chat for any questions. We'll have an awkward 2-minute pause before we start our second speaker. Okay, I'll just ask my very ignorant question, and please excuse me, but why is it that there are these periods of great activity at certain points and, not really much activity at the current time?
Yeah, fundamentally, I think there's many ways you could answer that question. The boundaries between sort of large lithospheric plates, like the eggshell plates that essentially cover the Earth, those boundaries change with time. In a lot of these images that we were looking at, sort of in the Triassic and the Jurassic, we had plate subduction in this area, and plate subduction means that we actively have different fragments of crust that are colliding with each other. When the motion of plates changes, I can get different types of boundaries, and right now we don't have that same convergence, that subduction in this area, not until you get out into the Aleutian Islands. And so there's just, there's less of a mechanism for bringing in new fragments of crust, essentially. But we do, there's a lot of activity in Kluane and in the ice fields where those mountains are rising very rapidly. And so there's still stress being kind of imparted to the crust, basically.
Okay, thank you very much for addressing what was probably a pre-intro geology question. And
those are always the questions that trip you up, though. That's, yeah.
And just a comment from the chat, just amazed how complicated the geological crafting of the western edge of North America is. Taylor's comment, and thanks for sharing. And there we go. So we're at 12:30 now. So thanks again, Joel. Really appreciate you taking the time to speak with us. And I'll introduce our second speaker.
Okay, thanks everyone.
So our second speaker today is Dr. Tara Stehelin, biology instructor and coordinator of the Renewable Resources Management Program at Yukon University. Raised in Yukon, maybe born in Yukon, not sure. Tara has a long history of research involving biodiversity and climate change, completing her Bachelor of Science in Wildlife Biology at University of Victoria, a Master's in Behavioral Ecology at University of Calgary, and a PhD in Conservation Biology in Yukon through the University of Alberta. Today, we'll hear from Tara about efforts to quantify and understand the impacts of climate change on migratory bird populations in Yukon. Sure to be an interesting talk, so let's get to it. Thanks for joining us, Tara.
Hi, thanks. You can hear me okay and see my screen? Yeah, okay, thank you. Thanks, Sabrina, and thanks for the invite. And thanks everyone for taking some time out of your busy lunch hour. So I'm affiliated, like Sabrina already mentioned, Yukon University, where I'm an instructor, coordinator, and conduct research when I can find time. Also affiliated with the University of Alberta, where I completed my PhD, but also continue to be connected to the Boreal Avian Modeling Project, which some of the members are based out of the University of Alberta. And I also wanted to just acknowledge and thank Kwanlin Dun First Nation and Ton Quechan Council for the opportunity to conduct research on and near settlement lands. Yeah, so one of the main reasons behind this research is really a declining biodiversity globally. So the biodiversity crisis that we're in right now and sixth mass extinction. And I'm particularly interested in birds. So recent analyses have suggested that 1 in 4 birds have disappeared from the landscape in North America since about 1970. And so we really need to study general climate and habitat changes resulting from these changes across the landscape and how this might be affecting biodiversity. So that represents, millions of birds that have disappeared, whereas the boreal forest does provide breeding habitat for about 300 different species of birds. So the big question is, can some of these regions of the boreal forest maybe provide some refugia from, changing climates, from intensification of land use, things like that. So that's sort of one of the big questions that I've been attempting to address throughout this last kind of chapter of my research. And I've been focusing recently on 2 species, the olive-sided flycatcher and the western wood pewee, and data from several different projects, such as breeding bird survey data, suggests that they're both declining precipitously. So widespread and long-term declines, although with some regional differences and how steep those declines are. And all aerial insectivores, so those are birds that consume insects, are declining in North America. So there's certainly a group of birds that deserve more study. So those are the 2 that I've been focusing on, and possibly hampering the ability for the boreal forest to provide refugia or places to reside, in the face of changing climates, is the rapid pace of climate change in our region. So, Canada has warmed twice the global average since about 1948, and Northern Canada 3 times the global average, and in parts of the North, even 4 times the global average of warming. So this potentially exposes species to novel climate conditions. So climate conditions that they wouldn't have a long evolutionary history with, and changes to community dynamics in the boreal forest. In addition, both these species, as with most insectivores, they migrate long distances. So both species migrate somewhere around 9,000 to 10,000 kilometers, the longest migratory route of any North American breeding tyrannid, which is just a flycatcher in this huge family of birds called the Tyrannidae. There's about 500 species of them. So these are the longest migrating of that group. And so this long migration potentially exposes birds to lots of different stressors along this long route. So changes to land use, deforestation in South and Central America, where they're overwintering, places like Ecuador, and intensification of agricultural practices from varying different, types of agricultural change. So all of this will influence prey availability, whether they can find, adequate stopovers to refuel and things like that, as well as just changes to insect populations that we're seeing all across this long migratory journey. So they spend more time migrating than actually in either their breeding areas or the overwintering grounds. So it presents a very significant risk, this strategy to move so far to take advantage of the huge food supply that we collectively provide for them in the north, and that's the abundance of insects that they arrive here for a short period of time and take advantage of to breed. So there's a lot of different factors potentially contributing to decline of aerial insectivores. Agricultural intensification, like I mentioned, so all sorts of different land use changes, an increased reliance on certain types of pesticides, like neonicotinoid pesticides, which the use of, has increased dramatically over the past several decades. It's gone up, the use of neonicotinoids has gone up 500% in Canada. So, that's going to impact, food availability for birds that eat insects, as well as forestry and fire management practices. And then, of course, climate change. So altered climate conditions, changes to range, changes to vegetation, and changes to interspecific interactions. So important interactions that species have with each other, such as predator-prey relationships. So these birds migrate from such a far distance away, they may not receive the right cues that spring is now occurring in the Yukon 2 or 3 weeks earlier. And so they arrive at the wrong time. So the community dynamics are different. And the insects that they rely on to feed their young may not be peaking at the same time they did historically, as well as a drying of water bodies. So many of these species, and these two are no exception, are associated with small water bodies because it supports higher abundances of insects, and their water bodies in the north are drying in response to changing climates, as well as just general changes to insect populations. So 51% of insect species in North America are declining, representing, a biomass loss of a recent estimate was around 2.5% loss of biomass per year, and changes to insect populations. So all of these things are influencing aerial insectivores probably, and it's not an exhaustive list. There's probably others as well. And I wasn't able to focus on all of these, so I've been focusing mostly on climate change impacts and changes to insect populations because of particular relevance where we are in an area of the boreal forest that's relatively undisturbed. So one of the techniques that I use to try to address the bigger picture questions, so the broad scale questions, looking at a broad geographic scale, is species distribution modeling. So we utilize huge data projects that are very collaborative and multidisciplinary and collect, data from hundreds of different projects, and to try to, look at prediction of important habitat or conditions that may predict longer term persistence of vulnerable species under changing climate and changing land use and changing insect populations and things like that. So what we do is through the modeling process, we associate bird data or any species data using occurrence, presence, absence, or we're very lucky in the Boreal Avian Modeling Project, we can use abundance data and associate it with various environmental predictors. So both, land cover and climate and topography and all these different things, and try to examine what will predict higher abundances. And then we can look at future climate scenarios and see where these species might be more abundant as conditions change. So that's what this very simplistic diagram is just showing. So looking at, whatever species you're interested in and environmental predictors, and then you can look at probabilities of occurrence and project them onto maps and, make predictions with this, of course, taking into account that there's going to be a certain amount of error when you're projecting into future time scenarios or into areas where we don't actually have bird data. So we have a lot of bird data that we can utilize in the Boreal Avian Modeling Project. At last count, somewhere around 1.5 million observations from 130,000 locations. And we're also very fortunate that it includes both on and off-road survey data. So we can look at, if there's any bias of surveys that are conducted on roads versus off roads, et cetera. So for this part of my research, I extracted about 15,000 abundance measures, where at least one detection of these two species was found. And then I used 7 climate and 7 land cover variables, and different vegetation layers, disturbance, some topography layers, and wetness under a current climate scenario, so a baseline with a median year of 1995, and then 2 future scenarios and 2 emission scenarios just for this exercise. And the type of modeling I use is boosted regression trees, which I can tell you about later if you're interested. And so some of the things we've been finding are that vegetation covariates at this geographic scale are very, very important in predicting abundance and distribution of these 2 species. And this is probably true for other aerial insectivores as well. So forested layers, multi-age trees were incredibly important, as well as complex topography and wetness. So riparian habitat, small water bodies, things like that. And then if we start to distill down, looking, in a little bit more detail at some of those layers and covariates that predicted relatively high abundance, low density forests really came out on top. Again, wet areas, riparian habitat, and regenerating forest. So something like, around 10 years following a fire predicted high abundances. And of course, climate variables are also very important, especially those relating to moisture and seasonality. So mean summer precipitation, for example, precipitation as snow. So snow layers are very important. And that spring melt and timing of spring melt is really important for the provision of some, insects in spring when birds are first arriving from such a long migratory journey. A number of frost-free days, things like that, as well as complex topography came out again and again as being very important in models. So sort of, sloping, which can lead to moisture pooling, which probably results in higher insect abundances in those areas. So those kinds of things. And then I just pulled out a couple results here, just looking at, because we can look at the different predictors and then really distill down, what are the specific things that seem to be resulting in higher abundances. So olive-sided flycatchers were really associated with low density evergreen forest, especially when we took into account the availability of that habitat class. So that's what this graph is showing. The lighter blue indicates that they were found in that area, in a greater abundance than would be expected given the availability of that habitat class. So the lighter blue indicates it's sort of a very, very crude measure of preference. Relative to availability, they're more likely to be found, in a low density evergreen forest, even though the highest abundance was actually predicted in medium density forest. But if low density forest is available, they seem to prefer that habitat type. And same with tundra shrub, which is also very open and often has a lot of moisture on the ground, and lichen bogs and old burns. So that certainly shows that, open forests are probably important. Multi-age trees, kind of this heterogeneity seems to be very, very important. And for just the other species, looking at a similar thing, western wood pewees were associated with riparian areas, especially when we took into account, the availability of that habitat class. And mixed open forest, grasslands, wetlands, tundra, and old burns. Again, mostly areas that are associated with a high level of wetness and groundwater and small water bodies and those kinds of things. So it's interesting if we just look at just predicted abundance, cropland actually comes out on top. But when we take into account the availability of other habitat classes, then they seem to be much more likely to be occupied, like old burns and riparian habitat and mixed open and things like that. So in general, it seems that heterogeneity in wet areas are very, very important, and multi-age trees. And then if we look at some of the projections and predictions for the olive-sided flycatcher. So that's just a few scenarios just to show you. So on the left panel, that's, the median climate conditions, so kind of a baseline. So you can see the darker green represents higher predicted abundance, and then the yellow is lower predicted abundance. So you can really see high predicted abundances in the west, in mid to high elevation. The Caribou Chilcotin, just huge in terms of predicted abundances, and parts of Alaska as well, central Yukon. And then I've just shown you one future scenario under a relatively high emission scenario with a median year of 2085. You can see, some of those areas are still very important, but there's definitely some differences, especially in Alaska. So terrestrial regions in Alaska have really changed, looking into future scenarios for climate. And there's a lot going on these projections. So the third panel is just simply the difference. So negative differences are in red, positive differences are in blue. So you can really see how there's a lot of negative differences in Alaska. So terrestrial regions are just going to become too hot and too dry to support high abundances of this species. And the circles just represent the geographic centroid. So it just shows that it's shifted north and west. And there are some positive differences, kind of the Alaskan Peninsula and a few other little patches around where there are some positive differences. So definitely some big changes from these results are predicted. For the Western wood pewee, they have slightly more of a southern distribution. So really high under the baseline, high predicted abundances again in the west, but a more southern distribution. Parts of BC really support high abundances. But then if we look at just one future scenario, we can see kind of a shift farther north. And it almost at first glance appears like a bit of an increase in abundance. But for a more southern distributed species, that could just represent some range shifting occurring. But again, we look at the difference, and there are large areas in terrestrial regions, interior Alaska and Western Yukon, where there's negative differences. So it certainly shows some predicted differences in distribution and abundance when we look at future scenarios. So the big question is, can northern boreal forest provide some kind of refugia for organisms as they face these rapidly changing climates? And the answer to that seems to be pretty specific to species from the species that we've been looking at. Just to show you the olive-sided flycatcher here. So unfortunately, the range that's filled has decreased. So the areas that are occupied decrease by about 15%. And shown in blue here are potential refugia, or areas that have higher than the average density under the baseline scenario. So that could be interpreted as refugia. And there are some areas, so dark blue areas would be refugia, yellow would be negative refugia, or basically inappropriate areas in this future scenario. Again, this is 2085. But there are some regions that could potentially provide refugia. Again, the Alaskan Peninsula, some interesting areas in central Northwest Territories, but overall a decline in abundance of about 30%. And it also begs the question as to whether these areas of refugia are too isolated from each other. So they're kind of in isolated patches. But it does, I suppose some good news can be gleaned from it as well, though. It's also making the assumption that vegetation change can keep abreast of climate change and still provide adequate breeding habitat for these species, which is a big question. So for the Western wood pewee, there's a percent change in area in the region of about 14% as they shift farther north. As a more southern distributed species, they have a bit more space, so to speak, to move a little bit farther north and occupy this area. I mean, again, we see some areas of potential refugia in blue, and coastal Alaska seems to come up as very, very important. and in parts of Northwest Territories and parts of Southern Yukon may provide some refugia for this species. But again, it begs the question of whether these areas of refugia are too small and too isolated from each other. And I've also been doing a lot of work at a more local scale on community and population ecology. So trying to examine climate change at the community level. So investigating phenology, so timing of breeding, and how that coincides with potential prey or insect abundance peaks and insect diversity. So trying to examine feeding habits and breeding success and how that might relate to insect abundance and diversity across the season. And I won't have time today to go through all of these results, so I'll just show you a few little things. So feeding observations and analyses that are ongoing to this day on prey availability so far seem to indicate a preference for large insects. So the pie diagram there just shows, what's available on territories. So hanging malaise traps that we have on bird territories show, a very high proportion of insects that are available, flying insects that are available are flies or Diptera. With much smaller proportions of the remaining Hymenoptera, which are, bees and wasps and things like that, and Lepidoptera, which are moths mostly and things like that. And then a very small percentage of odonates or dragonflies. And we've augmented this data also with, transect surveys that do a better job of capturing dragonfly and really, really large Diptera abundance. But nonetheless, it seems to show that, dragonflies are fed very disproportionately compared to, the availability. Mostly dipterans are available, but if dragonflies are available, they seem to prefer to feed their young that. So from very difficult to get feeding observations, very challenging, it seems that dragonflies are a preferred food. I think it's safe to say that now. And then also they're targeting large Hymenoptera, so the larger bees and wasps, and fairly large flies, dipteran, and then some are just unknown. It's hard to see the odd beetle. Beetles are interesting because when they do feed beetles to their young, they smash them up on branches first or a trunk of a tree, probably because the exoskeleton and the wing covers are so thick, the exoskeleton's so thick. And then Western wood pewees are a slightly smaller species, so it's even harder to get feeding observations. But from what we've seen, it's mostly relatively large Diptera, but also Hymenoptera and some Odonata or dragonflies or just unknown. And these are videos showing all-sided flycatcher female feeding her young. So you can see it's pretty difficult to see. We have to slow it down frame by frame and see if we can see what they're feeding their young. And this is a Western wood pewee feeding her young. So she's bringing, hopefully it's not too glitchy, bringing prey items in, and then she waits for a fecal sac and takes away the fecal sac. So hardworking parents. Yeah, so that was an unexpected finding, just how important things like dragonflies are, especially relative to their availability. They're not that abundant in numbers compared to other groups of insects, but seem to be very important. And just looking at just a few quick results with breeding success, just for a few years. If you focus on the red bars, that's the first nesting attempts. So first nesting attempts sometimes are abysmal. And that seems to be getting more so with year. So first nesting attempts with year seem to have lower and lower success rates. But then the blue shows the overall nesting success rate. Overall nesting success rate seems to remain relatively high, except for in 2021, where nesting success overall was almost zero. So I have to collect more years of data and see what the long-term trend is, but is something interesting going on, especially with first nesting attempts. And overall, just looking at a crude measure of insect abundance, just all insects combined, they seem to be declining in abundance with year, which also we need to look at more years of data, and we're going through some more insect data right now just to try to determine, is this a really, a long continuing trend, or were 2016 and 17 just terrible years? So that remains to be seen. But it does seem that insect abundance is declining with year. And then looking at asynchrony, so I don't have a lot of time to explain this, but basically it just looks at timing between energetic demands of the birds shown in blue and how that might be related to peak insect abundances shown in the red bars. So these findings have been a little bit messy and all over the place because insect abundance doesn't really have a well-defined peak at one particular day, probably because the diversity is so high here. We have so many different types of insects, and so there isn't really one particular week, that's the perfect time for the birds to be feeding their young. But we can still get a pretty good idea of timing using some modeling procedures, and it seems to show that some years are a bit early, like 2013 and 14. The birds were a bit early compared to insect peaks. 2015, they were kind of right on time. 2016 and 17, they were way late. So the birds were feeding young long after we saw most types of insects already peak. So again, this remains to be seen what the long-term pattern is. And then we relate that to breeding success. And it seems that timing is really important, but it seems that the highest breeding success is associated with if they're not particularly early or late. So sort of an intermediate or being able to be a little bit flexible seems to result in higher breeding success. And if I isolate different groups of insects, it seems that energetic demands from birds breeding seems to be very well timed with dragonfly abundance if we just look at dragonflies. So it depends how we look at the data, and there's more to be seen in the future with some of these questions. So for some conclusions, there's no really obvious predictable insect peak in the Yukon. There's no perfect week to be feeding your young, as a bird, but timing is important, or that flexibility around timing is really important. And birds are breeding earlier, but breeding success seems to be declining with year, especially if we look at first breeding attempts. And overall insect abundance might be declining with year. We need more years of data to say for sure. And back to the habitat and predictions, piece, wetlands, ponds, old burns, heterogeneous forest seems to be really, really important for birds breeding in the boreal forest. And that's all. Thank you.
Oh, thanks so much, Tara. That was great. I think we have one question in the chat that I think we have time for. It's from Mary. She's asked whether there's any project that's using your results for future planning, such as the NASA above the Arctic Boreal vulnerability experiment.
I hope so. I don't know. And we still have results that are constantly coming in. Like lately, I've been working on a modeling procedure that takes into account or takes the result of multi-species. I mean, usually they're aerial insectivores, but hopefully we can bring in lots of different types of species and look at intersections, and then determine what are the essential areas that we could protect. So yeah. I don't think NASA has my results. That would be amazing, but hopefully I'd be happy to share it with them.
Well, let's connect on that because they're always keen to connect with us. If you'll allow one more question, looks like Jim has his hand up.
Sure.
Hi there. Can you hear me okay?
Mm-hmm.
Yeah.
Yes.
It seems like from this that the insect monitoring the insects is extremely important here. Is there any kind of an established sort of long-term program that's been developed to monitor insect populations across parts of the range? Or we have the breeding bird survey, and we have a bunch of sort of bird things, but how about the insect part of it?
No, I don't think there's a widespread effort across different sort of a collaborative effort. There's people collecting information on insects, but they're all isolated from each other. So I think we have a need there too, because there's other bird researchers that I've been in, connection with that are also collecting insect data. So we've decided to, collaborate, but I think we need a much broader And I'm also not an insect expert, so I'm always looking for help. And I'm more of a bird person, so it'd be great to have, you know, more involvement. And I had, yeah, an entomologist keenly involved in this, but he's just retired. So there's also people retiring that we need, like John Spence.
Well, thanks so much. That was excellent. I'm sure we could have used more time for discussion on both talks today, and I appreciate you letting us go a minute over there, Tara. I know it's a busy time for everyone. Thanks for all who joined us, and I'm sure there will be folks looking for the recording, so I'll share that link in the next e-news, or if anyone wants it more quickly, you can certainly reach out directly to scope@yukon.ca. Hope to see some folks next week when we'll hear from Robin Mennel about caribou, Bathurst caribou population. A great afternoon.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you.